Hello everyone, welcome to Physics Pathfinder. In this video, we'll be solving theme E questions from past paper, and that is for paper 1 MCQ. So let's start. If you see this question, what is the sequence of evolution of a main sequence star that has a mass of about 2 solar masses? So if you compare this to the mass of a sun, which is called as a solar mass, the star in consideration is not very heavy. It is similar to the mass of sun because it is just 2 times the mass of sun. So it would pass the stages that a sun would pass. That is, it would go from red giant, then it would go to a blast, which is planetary nebula, and when the core is remaining, it will become a white dwarf. So the answer is the option B. Let's go to the next question. If you see here, you are given the spectrum of an atom. And this spectrum is naturally the light source. It's a light of different colors, which you cannot see here, but very clearly it's given that it is an increasing wavelength, which means the shortest wavelength is on the left extreme. This will be the shortest, and the one which is in the extreme, okay, will be the one which will be the largest. So we can tell that lambda 1 is lesser than lambda. Now we are supposed to look at lambda, the arrangement of the spectrum, and look at the energy levels that are going to be matching with these increased wavelength. As you see, the smallest energy level is down, which is level 0, and the highest energy level is at the top. We also know that E, the energy, is equal to hc over lambda, which tells you that energy is proportional to 1 over lambda. That is, if energy is decreasing, means wavelength has to increase. So if you look at in this extreme, the diagram, the wavelength are plotted in terms of increasing wavelength. So the energy that you should be getting should have a decrease. Okay, it is inversely related. So let's see. If you look at this gap, the wavelength has a bigger gap. The energy difference should be smaller. So we have two options here. Energy difference smaller is here as well as here. The next is the wavelength is extremely small, so the energy difference should be larger, which is going with A. If you see, the energy difference is larger here, followed by two small energy differences, which is again. So the first one is big difference, that is here. The next two is smaller, that's why it is here. And next is the bigger one again, which is also a smaller. So where the wavelength difference is more, energy difference should be less. Where the wavelength difference is less, energy difference should be more like this. So the answer for this is A. Let's do the next question. The photon of wavelength lambda scatters off an electron at rest. So there is an incoming photon of wavelength lambda. It hits an electron that is at rest. The scattered photon, so here we can see that this is the electron at rest. What happens? The scattered photon, so there are two paths. This is the scattered photon and this is the scattered electron. Okay. The scattered photon has a wavelength lambda dash. So the incoming photon was lambda. Scattered photon has wavelength lambda dash. What is the fraction of incident photon energy? So you need the fraction of incident photon energy, that is E in the side of input, whatever is this photon that has a wavelength lambda, what is the energy of that incoming photon? And that gets transferred to the electron. So they need the ratio of E input to E out. That is, what is the energy of the emitted electron? So the emitted electron will go here. That will have a particular energy. You can tell it as E dash. And the incoming photon will have an energy E. Now, what we know is E is proportional to 1 over lambda. Okay, what else? The photon has a wavelength lambda, scatters off an electron at rest. The scattered photon has a wavelength lambda dash. What is the fraction of E incident photon energy? So we need to find the fraction of E, which is the input part, over E of the scattered electron. So what is the answer? E incident, the fraction of incident photon energy that gets transferred to the electron. What is the fraction of incident photon energy that gets transferred to the electron? So if the total energy is lambda dash, the one that gets transferred is lambda dash minus lambda over lambda dash. So that gives you the option B. To the next question. The three statements about nuclear fission reactor are: the heat exchanger transfers energy from the fuel rod to the moderator. The control rods must be good absorbers of neutrons. Moderator must slow down neutron. So very clearly, moderator must slow down a neutron is correct. The control rods must be good absorbers of neutrons. That is also correct. Next one, the heat exchanger transfers energy from the fuel rod to the moderator is not correct, because the energy is transferred from the fuel rod to the working fluid, the medium that absorbs energy. It's not the moderator that absorbs the energy. So the one which has only 3 and 2 is option C. Now the Hertzsprung-Russell diagram, as you can see for the two stars, X and Y, is clearly showing that the luminosity is same. So what you can infer from this graph is the luminosity of X and Y is the same. You can see clearly. So we can start with L of X is equal to L of Y, which gives you the option. If you look at the data booklet, you will find the equation that luminosity is nothing but sigma A t to the power 4 for X is equal to sigma A t to the power 4 for Y. If I take it further, sigma area is area of a sphere, which is 4 pi Rx square, and we know the temperature of X is around 40,000 Kelvin. So it is 40,000 raised to 4. which is equal to sigma times 4 pi times Ry square times 10,000 raised to 4. Let's cancel out the common term sigma 4 pi. So what you're left is Rx square upon Ry square is equal to 10,000 over 40,000, the whole raised to 4. So if I remove all the zeros, I am left with 1 over 4 raised to 4, which is 4 to the power 4. 4 to the power 4 is nothing but 256. And if I take the square root of this, because Rx square over Ry square is 1 over 256, so Rx by Ry should be square root of 1 over 256, and square root of 256 is nothing but 16. So the option that you should be getting is 1 over 16, which gives you the option A. Let's take it further now. The energy of the nth level of hydrogen is given as. So if you look at for hydrogen atom, in the theory, it is derived very clearly that energy of the nth shell is nothing but minus E0 over n square, where n is the orbital number. What is the frequency of the photon that is emitted when there is a transition from level 4 to level 2? Which means from n is equal to 4, 3, 2, 1, and ground. So this is n is equal to 0, this is n is equal to 1, n is equal to 2, n is equal to 3 and 4. So when an electron jumps from level 4 to level 2, what you do is the energy difference, delta E, is always final energy level, which is level 2, minus energy level 4. It's final minus initial. To get the answer for energy at a particular state, you just plug in E0 over n square, which is n is 2 in this case. So your first step will be minus E0 over 2 square, which is 4, minus E0 over 4 square, which is 16. So if I open this bracket, it should be minus E0 by 4 plus E0 by 16. Multiply by 4 up and down. This will give you minus 3E0 by 14. By 16, sorry. Okay. Next is on a photoelectric effect. A monochromatic light of frequency F1 is incident on the metal surface. This is the metal surface. There is a photon that is incident and it has a frequency F1. The stopping voltage for this is V1, which will be a negative voltage. There is another metal, then the frequency of radiation is changed to F2. Now, instead of F1, if you are changing the frequency to F2, naturally your stopping voltage will change to another V2. The question is, what is the quantity V2 minus V1 over F2 minus F1? If we look at the photoelectric equation, you have the input energy, which is h nu, is divided into two parts, which is work function plus the maximum kinetic energy. Input energy, which is h into nu 1, and we know work function is nothing but the energy associated with threshold frequency or threshold, the energy associated with threshold frequency, or we can also tell that the stopping voltage is the one which will be affecting it. Then the work function will be 5, and the maximum kinetic energy would be proportional to the stop. E B1. Same way, H nu 2 should be stopping. Similarly, H nu 2 should be the work function plus E B2. Now they are asking you to get the answer for V2 minus V1 upon F2 minus F1. So we subtract EV1 from EV2, which gives you the equation EV2 plus 5 minus HF2 is equal to 0. The next step is EV1 plus 5 minus HF1 is equal to 0. I subtract these. This will give me the equation EV2 minus EV1. The next being minus HF2 plus HF1 is equal to 0. I'll take it out, so it will be V2 minus V1 minus, if I take it out, HF2 minus HF1 is equal to 0. Take this on the other side, you will be getting E2 minus V1 is equal to H taken out, F2 minus F1. Dividing both the sides by F2 minus F1, what are you getting? P2 minus P1 over F2 minus F1 is equal to H by E. So the answer has to be C. Alpha particle, which is nothing but a helium nucleus of initial energy 5.5 mega electron volts, moves towards the center of a nucleus of gold that has 79 protons. What is the distance of closest approach? So to find the distance of closest approach, it's nothing but finding R0 when you're given the input energy. So the first step is we are going to convert the input energy from 5.5 MeV to joules, which is 5.5 into 10 to the power 6 Electron volt to joule is 1.6 into 10 to the power minus 19 in joules. So you're given energy. Now when the alpha particle is coming closer to the gold nucleus, the energy conversion is at a distance it has kinetic energy, but by the time it reaches closer to the gold nucleus, there is a point where it stops moving. So the entire kinetic energy is here converted to potential energy. And this distance where it retrieves the path, it goes back to the same position from where it started. The energy conversion is, or the distance between that alpha particle and the nucleus, is that R0, which is the distance of closest approach. So alpha particles don't go closer than R0 because of repulsion. So what we can do is this energy, we can equate it to the potential energy, which is A capital Q small q over R. And here this R is nothing but R0, which is the distance of closest approach that they are asking. So swapping the position of energy, we get R0 is nothing but K capital Q small q over the energy. Substituting the values, what it will be is K is nothing but 8.89 times 10 to the power 9. Capital Q is the bigger charge, which is 79 protons. So you have 79 Z, and the value of each proton is E, which is 1.6 times 10 to the power minus 19. Alpha particle has two charges, so it's 2E. So if you see, there are E into E for each of them, so it becomes E square divided by the energy that we have here is 5.5 into 10 to the power 6 into 1.6 into 10 to the power minus 19. One of this get cancelled here. When we do the calculation, we get the answer, which is B. So with this, we complete our today's topic, which is solving the E-based paper 1 questions. And this is from the sample paper given for 2025. Thank you.